from the subject Applied Hydraulics. In that first module is Dynamics of Fluid Flow. And the dynamics of fluid flow means what? The dynamics of fluid flow is the study of fluid motion with the forces causing the flow. As all of you know that according to Newton's second law, force is equal to the mass into acceleration. So according to Newton's law, suppose I am going to consider the force along x direction, then Fx is equal to mass into acceleration along the x direction. This force Fx, according to the Newton's law, Fx is equal to m into ax, where force along the x direction is equal to mass into acceleration along the x direction. There are the following forces acting on the flowing fluid. In that, first force is Fg, that is gravity force or gravitational force. Then second force is pressure force. Fv means force due to viscosity. Then force due to turbulence, that is Ft, and Fc is equal to force due to compressibility. So net force acting on a fluid flow is equal to Fx, that is net force, Fg plus Fp plus Fv plus Ft plus Fc, if when the fluid is incompressible. The fluid is incompressible means Fc becomes 0. Then the equation becomes Fg plus Fp plus Fv plus Ft, and this equation is called Reynolds equation of motion. If this Ft, that is the force due to turbulence, if Ft is equal to 0, then the equation Fx is equal to Fg plus Fp plus Fv, and this equation is called Navier-Stokes equation of motion. The viscous force is 0, then the equation becomes Fx is equal to Fg plus Fp, and this equation known as Euler's equation of motion. And as all of you know that Euler's equation of motion is very useful for the real fluid as well as the ideal fluid. And in the last year already we had derived the Bernoulli's equation from the Euler's equation. Now we are going to see the momentum principle. The statement of momentum principle is that the net force acting on a fluid mass is equal to the change in momentum of flow per unit time in that direction. So here we are going to see the expression how this statement, according to that we are going to see its equation or mathematical form. So according to Newton's law of motion, force F acting on a fluid mass is given by this equation. This equation all of you know that F is equal to m into A. So this force F is equal to m, as this is the acceleration. The acceleration can be write in this way, that is dv by dt, change in velocity with respect to time. So I can write this equation m into dv by dt. So this can be write in this way, d m into v into dt, where m is constant. What it indicate? The force is equal to change of momentum with respect to time. This equation, suppose this is the equation number 1. This equation is called momentum equation. This equation 1 I can write in this way also, F into dt is equal to dmv. What it indicate? The F into dt, this is nothing but impulse, and this is rate of change of momentum, So this equation 2 is also called impulse momentum equation, because impulse means it is the product of force into time. Okay. Force exerted by a flowing fluid on a pipe bed. Last video we know the impulse momentum equation. By using that impulse momentum equation, we are going to derive this expressions, means we are going to find out the force exerted by a flowing fluid on a bent pipe. Suppose here I am taking a reducer pipe, or we can say as it is a bent pipe. Why it is reducer? Because you can observe here the cross section of the pipe is large than the cross section at section 2. Reducers means what? All of you know that when a pipe is attached with the nozzle, so nozzle part is a reducer part and the pipe having the cross section 1, 1. So now when the fluid is flowing through this bent pipe, we want to find out the force exerted along x direction and force exerted along the y direction. Before finding out this fx and fy, we should know what are the different types of forces acting on this bent pipe. So here we are consider the two sections as section 1, 1 and section 2, 2. Along this section obviously the pressure force. It is a pressure force. P into A1. This is the pressure force at this section. So, the P1 A1 is a pressure force at section 1 and with velocity is V1. When we are going to consider at section 2, the pressure force will act on the section 2, but it is in opposite direction, that is called as P2 A2. So for your simplification, I am going to resolve this force here, which makes an angle of theta with the horizontal. So this P2 A2 resolved along the x direction and y direction, that is P2 A2 cos theta and P2 A2 sin theta. Similarly, here you can observe at section 2, the flow will pass through the section 2 with the velocity of V2. And this velocity makes an angle of theta. So, it having the two components, V2 cos theta and V2 sin theta. Okay. So, now along these forces, as per the Newton's third law, there is, when the flow is flowing through this pipe, obviously the reaction will be taken by the bend, or reaction force acting on the flowing fluid by the bend. That reaction, opposite reaction, which is exactly equal and opposite to that horizontal force, that is minus Fx. Similarly, along this direction, the reaction force will be minus Fy. So, here we are going to resolve the forces and finding out the Fx and Fy, that is the force exerted by the flowing fluid on a bent pipe. So, according to impulse momentum equation, net force along x direction is equal to the rate of change of momentum. So, net force along the x direction. See here, this P1 A1 along the x direction. So, P1 A1. Then P2 A2 along the x direction, but it is in negative. So, P2 A2 cos theta. Then here this reaction along the x direction, that is minus Fx, is equal to mass per second into change in velocity, that is rate of change of momentum. Here mass per second means we are considering the mass flow rate. So mass flow rate is nothing but rho into Q. Rho is nothing but density. Q is the discharge. And the change in velocity. Change in velocity means final velocity minus initial velocity. So, here this will become rho Q. Here final velocity will be V2 cos theta minus this V1 is equal to P1 A1 minus P2 A2 cos theta minus Fx. So from this, Fx becomes rho Q V1 minus V2 cos theta plus P1 A1 minus P2A2 cos theta. This will give you the horizontal force exerted by a flowing fluid on a bent pipe. Now, after finding out net force along the x direction, then we are going to find out the net force along y direction. So, according to the impulse momentum equation, consider the net forces along the y direction. See here, how many forces are acting along the y direction? This is P1A1, it is only along x direction, so here becomes 0. Then you can consider this force, that is the P2A2 along the cross section of 2, but it in downward direction, so P2A2 sine theta, then minus Fy, this downward direction force, that should be equal to mass flow rate into change of velocity. So mass flow rate is rho q, change in velocity. Change in velocity means final velocity minus initial velocity. So here final velocity is v2 sine theta minus, here only along x direction, so this becomes 0. Along the y direction, so the net force along y direction will get here rho q minus v2 sine theta minus a2 p2 a2 sine theta. From this we can find out the force along the y direction. So after getting fx and fy, we can find out the resultant with the help of summation f of x square plus summation f of y square by using this formula. And to find out the direction, or the resultant force makes how much angle with the horizontal, for that purpose we can find out the theta by using this formula, tan inverse of fy upon fx. So here we got the flowing, a force exerted by the flowing fluid on the bent pipe.